Yes. Okay, everyone. Hope you can hear me. So welcome to the first session today in TPMPC. The first speaker is invited speaker, Gilboa from Ben Gurion University. He has his PhD from Technion originally and is now at Ben Gurion, as I said. He has a whole bunch of interesting results behind him on distributed point functions, private information retrieval, etc., etc. And today we'll hear about efficient, fully secure computation by distributed zero-knowledge proofs, a joint work with Alan Boyle, Yuval Ishai, and Ariel Noff. Over to you, Niv.
Okay, thanks a lot. Can everyone hear me?
Yes.
Yeah, I hope so. So thanks for inviting me, and thank you for everyone who's attending the talk. So I'm going to talk about two works. Both are with Alet, Yuval, and Ariel. One is already published. It's fully secure computation for fully secure three-party computation via distributed zero-knowledge proofs. And the second is a newer work. It's efficient, fully secure computation, again, via distributed zero-knowledge proofs. It generalizes the three-party computation to any constant number of parties. And one of the main tools we're going to use is from previous work with Dan Bonnet and Henry Corrigan-Gibbs on fully linear PCPs. Okay, so I'll start with an overview of what I want to talk about and the results. So here's the goal. We have standard MPC. There are n parties. Some of them are good, some of them are bad in pink. And they want to compute some function f. And we're thinking about a semi-honest MPC. And our goal is to turn this into malicious MPC. So now the bad parties aren't in pink, they're in red. They're actually really nasty. And we're going to follow the GMW paradigm. We're going to run the semi-honest protocol and then have everyone prove that they worked correctly. And the point is that the communication is going to be very low. The communication is going to be little o of circuit size. That's our goal. So the semi-honest protocol will be some big O of circuit size communication, but the compiler will only add some sublinear communication. And asymptotically, the malicious communication will be about as much as the semi-honest communication. Okay, so a little more on our setting. This is the setting of honest majority. So you can think of this as a complement to Kermit's talk from 2 days ago. She talked about the dishonest majority and was also interested in improving communication complexity, and her work with others got to a factor of 2 between the malicious and the semi-honest. And we're going to talk about the honest majority setting. So the number of malicious parties is strictly less than half of the parties. And we're going to get a little better. It's going to be there will be sublinear addition in the compiler. But the number of parties we're going to deal with is a constant. We're going to talk about circuits over any finite field. So that includes large fields, or F2 for Boolean circuits, small fields, anything goes. And for rings, the interesting rings of integers modulo a power of 2, or any other modulo, integers modulo any other n as well. Our main measure is communication. So we're thinking about a circuit with some number S of multiplication gates. And the semi-honest protocol, its communication is going to be large O of S. We're going to be interested in the exact constant there. This work is about constants, and I'll talk about that more during the talk. And the malicious protocol will have an additional little O of S. We're interested in concretely practical protocols. So the security is based on any PRG. We're not going to use any kind of public key encryption. Okay, so we can think of different flavors of malicious security. I'll mention 2 here. One is security with abort. So we have some incorrect execution. The parties realize it's incorrect. We try to find who the bad guy is, and we have the usual situation in corporate environments, maybe in universities too. Everyone's pointing the finger. We don't know who the bad guy is, and the only thing we can do is abort. And here we got denial of service. We can't finish can't complete the computation. And the stronger flavor we're interested here is full security or guaranteed output delivery. Okay, so this is the main theorem we achieve. Here it goes. If n is constant and t is less than half of n, so in the honest majority setting, and if f is, as I said, defined over an appropriate ring, and f has s multiplication gates, then there exists a fully secure protocol in which the communication is less than 1.5 ring elements per party per gate. Okay, and as I'll show, that matches the best semi-honest protocol we know. Okay, so this is the main result. And to give some examples, if I stick this specific numbers, so if I have n equals 3, so that's a 3PC, and 1 corrupt party, then the communication complexity is going to be S, strictly S, plus little o of S elements per party. And for 5PC, that's 2 corrupt parties, we're going to have 6 over 5S plus little o of S. Those are the concrete numbers. The 3PC, we actually have an implementation, or most of an implementation, and we have, I'll speak about the numbers a bit. We're going to go over that. That's a secondary theorem, which I'm not going to spend time on. There's been some recent work in this area. We're not the only people working on this. And this This has been published on an ePrint a couple of months ago, and I believe will be published in conferences soon. So this is by Goyal, Song, and Zhu, and their work is a fully secure protocol for any N, which has, it's also interested in reducing communication complexity. It has 5.5 field elements per party if none of them cheats, and it's a bit worse, 7.5 field elements per party if someone does cheat. So comparing these two works, our work and this work by Goyal and others, so our work is better for a constant number of parties by a factor of about 4 or 5. And our work is good for rings. Theirs isn't. Their work is better for many parties. As I'll show, the communication complexity deteriorates for us when the number of parties grows and theirs doesn't. They use a completely different techniques, and the results are different. Resulting protocols are different. Okay, so I'd like to talk a bit about the components we use in our work. So we all know about zero-knowledge proofs. This is classical from the work of Goldwasser, Micali, and Rockoff in the 80s. So what do we have in zero-knowledge proofs? We have a prover and a verifier, and the prover wants to prove some statement to the verifier. So the prover, say, they both have graph, and the prover wants to prove that the graph is 3-colorable. So they engage in a protocol, and at the end of the protocol, we want the verifier to know that G is 3-colorable, but nothing else. Specifically, we want the proof to have 3 properties. It should be complete. So if P is honest, it convinces, and V is honest, P convinces V. It should be sound. So if P is dishonest, then it can rarely fool V. And it should be zero-knowledge. Even if the verifier is dishonest, then only learns that G is 3-colorable and nothing else about G. Okay, so this is a classical notion in crypto. I want to talk about a newer notion. This is from our work in last year with Dan Bonnet and Henry Corrigan-Gibbs. So this is zero-knowledge proofs on distributed data. What's the situation here? We have the same prover. Okay, it wants to prove some statement, but now the verifier doesn't have the input. In fact, there are several verifiers, and the input is distributed between the verifiers. So here we have V1 and V2, and V1 has graph G1, and V2 has a graph G2, and together in some way they're the original graph G, but each separately is not G. Now the prover wants to prove that the sum of these two graphs is 3-colorable. So we want the same type of properties. We want completeness. So an honest P can convince V1 and V2. And we want soundness. A dishonest P rarely fools V1 and V2. But in the zero-knowledge, we want something a bit stronger. Not only should V1 and V2 learn nothing about nothing beyond the fact that G is 3-colorable, we don't want a dishonest V1 to learn anything about G2 and vice versa. Okay. A specific and an interesting instance of zero-knowledge on distributed data is zero-knowledge on secret-tier data. So here we have some language L. We can think of a finite, it's in a finite field F or in a ring, both are okay. But now we think that the input X is secret-tiered. So the prover has X fully, and the verifiers have shares of X. So together, if they reconstruct the secret, they have X, but each one separately doesn't have X. And now the prover wants to prove that some statement on the reconstructed secret. So x1 plus x2, which is X, is an L. Okay, now when the most interesting situation for general zero-knowledge proofs, or the beginning of this field, was proving very difficult statements. NP-complete statements, for instance, such as the fact that G is 3 colorable or is not. But in this talk, we're not interested in proving very difficult statements. We're interested in proving some statements on very simple languages. Specifically, we're going to talk about languages that are some degree 2 relation. And what we want to do now is not to show that it is feasible to prove something, but that we can run this proof, and the proof itself is sublinear in the size of the statement. That's going to be the interesting goal for us. And eventually that's going to lead to the point that we can compile a semi-honest protocol to a malicious protocol with sublinear communication. Okay, so suppose we have this distributed zero knowledge. How can we use it in an MPC? So here's our approach. We start with a semi-honest protocol, and here's the original circuit. There's some circuits over a ring. There are a bunch of addition gates and a bunch of multiplication gates. And we have the input. And there's some secret sharing of the input. And we want this secret sharing to be robust. I'm going to go back to this several times during the talk. By robust secret sharing, I mean that the honest parties by themselves can reconstruct the secret, which is what we have for in an honest majority setting. Okay, so the input is shared, and then the parties start to evaluate the circuit. So they go over it gate by gate, and every addition gate is evaluated locally. And there's some private protocol to evaluate multiplication gates. And after all of this, we can have, there are quite a few protocols in the literature in which the whole thing is evaluated. And just before the output is sent, none of the parties know anything. What they've seen so far, basically only uniformly random strings. And then they have one round to send the output. So suppose we have this kind of semi-honest protocol. What we're going to do to turn it into a protocol that's secure against malicious adversaries is to have a second step, a distributed zero-knowledge proof, and we're going to stick it right here between the evaluation of the circuit and the output. And we're going to ask the parties to prove that the messages they sent were correct. And if this proof is sublinear in the circuit size, then we've achieved our goal. Okay, so what is it that we prove exactly? For each multiplication gate, we have secret shared output, we have input, we have secret shared output, and the message is some degree 2 mapping of the shared input and the randomness, allowing to derive the shared output. So one example is the original BGW protocol. That's exactly the way it works. So the proof is going to be, it's going to look at all of these messages, and it's going to prove that all of them were processed correctly. So the output for each pair of inputs is indeed the correct degree 2 mapping.
Neil?
Yeah.
Just a small question here. So if you go into one of these gates that are in the middle of the circuit somewhere, it's of course true that the inputs to that gate are secret shared, and so is the output. But there's no single prover who knows all those shares. So how does that fit with the model you described earlier? Because there you were saying that there was one prover who knows the secret.
Excellent question. So what we want to do is not that there is one prover who knows everything, but each prover or each party is going to prove separately that its own messages were computed correctly. Okay, and then we get that everything was done correctly. But that's an excellent question, because the difference between one prover knowing everything and all of them together knowing something is going to figure later in our protocol. It's going to cause us some serious headaches. Okay, so so these parties sent the proofs, and we have 2 cases. If the proof was successful, then everything's great. We can send the output. But what happens if the proof fails? Okay, now we're in trouble, because, as I said, abort isn't good enough. We need something better than abort. So we're going to use the following concept. We called it semi-corrupt pairs. I think it's been used it's been called player elimination in the literature. I know of some papers that used it in the past, but I couldn't find one definitive source for all of them. So I hope I'm not annoying anyone. Here's the idea. This is what we want. We want to identify a malicious party. And once we have the malicious party, we can kick that party out. So here's the malicious party. It's obviously a bad guy. We're going to pillory him and continue the computation without him. But in our protocol, we don't achieve that. Here's what we get. We get a semi-corrupt pair. So here's one reference from Hirtmauer and Przydatek from 2000, and I believe there are earlier works with the same idea. We're going to have 2 guys. One of them is going to be a prover, and one is a verifier. And this occurs when one of the provers tries to say that all the messages he sent were correct, and then one of the verifiers says, broadcasts to everyone, no, these messages aren't correct. There's some inconsistency. So once we have that situation, what we know is that one of them is malicious. They can't both be honest. So as soon as we have 2, we're going to kick both of them out. And this is good enough for us because we're in the honest majority setting. So if we kick 2 out, we're still in the honest majority setting, but with n-2 participants, and t-1, at most t-1 malicious participants. And we can continue doing that until we have only one party, and that party is going to be honest. So here's a basic approach. We're going to start in rounds. So the first round, we're going to have some verifiable secret sharing with the threshold T of the secrets. We're going to run the semi-honest protocol, and we're going to have distributed zero-knowledge proof where every party proves that his messages were correct. And for that, we'll need the fact that the honest verifiers together have a secret sharing of each of the secrets are all robustly shared. So the honest verifiers together have a secret sharing of the messages of each of the corrupt parties. So when a corrupt party tries to cheat, that will be caught by the honest verifiers together. So they're going to communicate, and one of them will say, no, this is wrong. And now we have a semi-corrupt peer. We have a prover and a verifier, and one of them is dishonest. So in this situation, we're going to have a second round. And now we're going to ask this pair of parties, P and V, to reshare their input, but now with the lower threshold, with the threshold T-1 among the other parties. And we're going to run the same protocol again. And we can do this time after time, at most T times. Each time we're going to kick out at least one malicious party. And at the end, we have at least one party standing. And that last party is going to be honest. And this guy can output the result. OK, so this approach works. There's only one little problem. I got you sitting here to listen to my talk because I claim some efficiency. But I claim that the communication is going to be less than 1.5 ring elements per party per gate. But here we have a semi-honest protocol, which is some large O of S communication. We have the number of iterations is T. And the distributed ZK protocol, I haven't even shown that it works in sublinear time. So we have at least T times S communication. And T can be larger than 1.5. So this doesn't satisfy what I claimed. So I have to show you something a little bit better for you to take me seriously. So let's start with semi-honest protocol. I'm going to show a semi-honest protocol that achieves less than 1.5 ring elements per party per gate. So I'll start with a short reminder on replication-based secret sharing. This idea is from ISN 89. And it's very simple. We have n parties. We have a threshold of T and some secret S over a ring. And we have many shares. For each subset, T, which is of size n minus T, we have one specific share, xt. And all these shares together, if we sum them up over the ring, we get the secret S. And party P receives this share xt if P is in the set T. The point is that if we have some malicious party with T participants, they're going to miss at least one of the shares, because all the other guys are going to get that share and the malicious party will not get it. The downside of this secret sharing is that the number of shares is large. It's n choose T overall and n-1 choose T per party. And this is exactly the reason that we're limited to a constant number of parties. N is the number of parties, T is the number of malicious parties, and as n grows, the number of shares grows exponentially. But if we talk about a small number of parties, say 3 or 5, this is very reasonable. And the reason we like this type of secret sharing, or in many previous works on MPC it was used, is that it's very useful for compressing correlated randomness. So if a set of parties wants to have a very long random string that's identical among all parties, they just have to share one seed. And previous works from 99 or CDI, Kramer, Daumgarten, Nishai from 2005 discussed this in the context of MPC, of share conversion, and so on. In a way, replication-based secret sharing is the most basic linear secret sharing scheme. Okay, so we're going to use this replication secret sharing to massage a bit Daumgarten-Nielsen protocol. We showed how to do that in the work with Dan and Henry. And what we want is a semi-honest private multiplication with honest majority that works as follows. So we're going to do one multiplication. We have two secrets, S and S prime. S is a sum of these shares xt, and S prime is a sum of these shares yt. And we want to multiply them together. Now notice that when we multiply S and S prime, we have a sum of many terms of the form xt times yt prime. And because we're talking about an honest majority, each t is of size t plus 1, each of these sets. So there exists at least one party that has both the share xt and the share yt prime. And that party can compute the product locally. And then we have to sum all of these products together and reshare. So this is the way it's done. I show three parties here. We can think of many parties. The two guys on the right have this is party P. He has xt and yt, and he has some seeds. And the other party P prime has xt prime and yt prime and some seeds. And each of them is going to sum up all of these terms that it knows and mask them. So one guy sends sum of xt yt plus some mask mp, and the other guy sends a sum of xt prime and yt prime plus some mask mp prime. They send all these terms, all these masked terms, to one party, the aggregator, and he's going to compute the actual result, which is S times S prime, but masked. So once he computed the masked result, the masked output, he's going to reshare resend the shares. Now, for most of the parties, the new share is going to be derived without communication. So for all the parties that the aggregator is part of, except for one party, for all of them, the new share is going to be random, and they're going to derive it from their pseudo-random generator. For one party, the aggregator is going to send a correction of what he got minus all the pseudo-random shares. He knows these pseudo-random shares because he also shares the seeds. Then all of the other people, except the aggregator, they know the mask because that was random. They're going to unmask their share. So now they have a new share. And for any set in which the aggregator, in which the aggregator isn't part of, these shares are going to be 0. So how much communication do we have here? In step 1, we got one ring element from each party except for the aggregator, so that's 2t elements. And step 2, the aggregator sent one ring element to all the other participants in one set, so that's t ring elements. Together, we have 3t per gate, and that's less than 1.5 per party. If we switch around the roles of the aggregator, it's really going to be less than 1.5 per party, not only in an average sense. So this is our notion of the replication DN. So that's one part, the semi-honest protocol. To get to the second part, we're going to need to talk about distributed zero knowledge, and we're going to do it via fully linear PCP. So here's the notion. Linear PCPs were introduced by Yishai Kushilevitz and Ostrovsky in 2007, and here's the idea. So we have a prover and a verifier, and there's some statement, there's some input X, and the prover wants to prove that X is in a language L. And so the prover constructs a proof, pi, and the verifier can't see the proof. The only way it can interact with the proof is send some vector Q and get back the inner product of Q and the proof. Can do it several times and can use that to convince itself that X is an L. So that's an older work. In this line of work, we're going to talk about fully linear PCP. It's not only linear, it's fully linear. And the difference is that now the verifier doesn't have access to the proof pi, but it also doesn't have access to the input X. So the only access it has is to send linear to generate vectors Q and get the inner product of Q and the input X concatenated to the proof pi. And this is going to be great for us because in our case, we want to prove statements about input that's secret shared between other parties. So the verifiers don't have access to the input. They in fact will have only linear access to this input. Okay, so if I want to argue that if a language L has this fully linear PCP, then can also have zero knowledge proof on distributed data. So how does this work? The prover generates the FL PCP proof, the fully linear PCP proof, and splits it using secret sharing. So one verifier originally has pieces of the input, x1, x2, and the prover generates pi, splits it into pi1 and pi2, and now the verifiers have x1, and the first one has x1 and pi1, the second one has x2 and pi2. The query is whatever it is, and now they can publish shares of the query answers and reconstruct using the same reconstruction of the fully linear PCP. So if we have the fully linear PCP, we also have distributed zero knowledge proof. Given these answers, they can both, they have the same answers, they can both be convinced that X is an L. Communication is the size of the proof plus the small number of answers that they've exchanged. It's going to be very small. So what we show is that we can do proofs on structured circuits that are very short. So what do I mean by structured circuits? So we can think about some fields. It also works for rings. And L is a language in Fn. And G is some algebraic gate. It's going to be a large gate with a low degree. In our case, the degree will be 2. And so its size is L. That's fairly large. In our case, it's going to be square root of n. And the degree is low. In our case, 2. So the theorem we show is that if a language L is recognized by a circuit that has m G gates and whatever number of addition gates, then there's a zero knowledge proof that has a constant number of rounds, and the communication cost is going to be the size of G, L, plus m, but times the degree of G instead of the size. So instead of talking about a linear, a proof that is linear in the size of the statement, it's going to be, in our case, only quadratic in the size. So for degree 2 circuit, we have a multi-round protocol, log n rounds with very low communication cost, only log n. And we also have a generalization with k rounds and communication cost n to 1 over k, which is going to be used here, 2 rounds and communication cost square root of n. Okay. I'll just briefly show the idea how this is done. So on the right, you see structured circuits. We have this circuit with a bunch of G gates. And we're going to order the gates. So we have some specific order. And you see that G3 is the output gate of the whole circuit. And we're going to define polynomials. So polynomial FL is going to be defined by the left wire, the left input wire to each gate. So FL of 1 is the left input wire to G1, FL of 2 is the left input wire to G2, and so on. FM, F middle, is going to be the middle input gate to each G gate. And FR will be the right input gates. So these are the input polynomials. We're also going to define one output polynomial. G, as you recall, is some algebraic gate. And P is going to be the operation G composed with all of the input polynomials. So now P actually, its values are the output values of the gates. So P of 1 is exactly the output of G1. P of 2 is the output of G2, and so on. And P of the last gate is the output of the whole circuit. Okay, so now if the prover sends P to the verifiers, then the size of P is the number of G gates times the degree of G, which is, in our case, is going to be a square root of the circuit size. The verifier has to check two things: whether P, the output of P, is 0, which means that X is in the language, and whether some P on some random input is in fact the value given by running G on this random input. Both of these operations can be done by linear operations because they only require interpolation and evaluation of polynomials. So they're linear, and therefore they can be done via FLPCP and via the distributed ZK. Okay, for ZK, we have an extra randomization of the polynomials with a random free coefficient, but that's small detail. The corollary we can see down below. We can get a proof size that's I'm sorry about the n here. It should have been circuit size. It's 2 times square root of circuit size. That's the size of the statement. Okay, So now when we have the components, we can show how to do the fully secure MPC, and this time efficiently. The previous time, the basic approach was inefficient. So here's what we do for 3PC. We first secret share the inputs. We run the semi-honest protocol using the replication Damgard-Nielsen I showed. Above it, we run the distributed ZK. Each party proves that its messages were consistent. If the consistency checks, if the distributed ZK returns accept, everything is good. And if not, we have a semi-corrupt peer. Now, these two guys, one of them is dishonest. And in the 3PC with honest majority, there's only one dishonest party. So we know for a fact that the last guy, P3, is honest. So both parties can send their inputs to that party. It can locally compute the function and release the output to everyone. Here are some numbers from our implementation. So we checked this for a circuit with 1 million gates, and compressing the proof as much as possible, we got it down to ½ kilobyte of communication. Soundness is 2 to the minus 40, and the computation now becomes larger. The bottleneck is the proof and the computation, all the linear operations to evaluate and to interpolate the polynomials. And we have about 30 field operations per gate. Okay, here's some comparison of our 3PC protocols with other protocols. Our work is the bottom row. And as you see, it's fully secure, and it has exactly 1 ring element per party per gate, better than all the others. What happens when we want to do NPC with n greater than 3? So sadly, we have some complications, some of them hairy. I'll go over them very briefly. I'm not going to go into the details. But here's we're coming back to the point that Ivan talked about earlier. Distributed ZK requires that the honest verifiers share the statement of the corrupt prover. If n is greater than 3, that's no longer the case. The aggregator, when he sends his message, it's a sum of the inputs of all of them, of all the other parties. And if some of the parties are, some of the verifiers, the other parties, are dishonest, then the honest parties don't have a sharing of that prover's message. That's one problem. And the second problem, which I haven't solved yet, is that we have T iterations of the semi-honest protocol. And if T is greater than 2, then the communication is at least double what I promised. So solution to the first problem, which I'm not going to go to, is that we can have the same distributed zero knowledge protocol I showed can be done with distributed provers, assuming that the inputs are robustly shared and that the outputs are a degree 2 function of the inputs, which is the case for our proof. So we can distribute the provers, and instead of having one prover prove the consistency of its own messages, we can have all the provers together proving the consistency of all the messages. But now we have a different problem. There's no semi-corrupt peer. If we don't have one specific prover trying to prove a statement, then we don't have a verifier that can accuse that prover. The thing is that distributed proof itself, with the distributed prover, that does have the right structure for having each of the provers prove its own actions during that stage on its own. So now we're going to have the following structure. We're going to have the secret sharing. We're going to have the semi-honest protocol. We're going to have the distributed provers version of a distributed ZK protocol in phase 1. In phase 2, we're going to have each of the provers separately proving that its actions during phase 1 were consistent. So if in phase 2 we got a reject, that's good. We have a semi-corrupt peer because each prover worked separately. And if in phase 1 we had a reject, we still have to work some more to get a semi-corrupt peer. And the way we do it is we localize the failure. We have to find where that failure is. And we do it by some binary search on the semi-honest protocol. We find one inconsistent gate, and we run any fully secure MPC. It doesn't really matter. It can be, because it's done only T times, it can be inefficient, that outputs a semi-corrupt peer on that gate. Total communication is still a little low of us. And reducing the T rounds, we move to a block structure, which has also been done many times in the past. Instead of having one semi-honest protocol, we have many segments, many blocks of semi-honest protocols, and we prove each one separately. So if in one of these segments we have an inconsistency, we have to go over only that segment. Taking the number of blocks to be large enough, which is about n squared, we again reach a sublinear communication. Okay, we have another issue, an authentication tag per set per block. I'm not going to go into that. In summary, we start with the semi-honest protocol, which has less than 1.5 ring elements per party per gate. We throw in distributed prover, distributed zero knowledge, single prover, distributed zero knowledge, binary search to localize faults, block structure, authentication tags, and after all of this, we have the gall to call our idea natural protocol. But with all of this machinery together, we do get fully secure MPC with less than 1.5 ring elements per party per gate, which for Boolean circuits is 1.5 bits per party per gate. What's still open? Well, minimizing communication for any n is still open. There's still a gap between what we can achieve for a constant number of parties and the Goyal, Song, and Zhu paper for any number of parties. Optimizing computation is pretty much open. Our ideas reduce communication and add to the computation. And for dishonest majority, we'll need totally different ideas. Instead of the semi-corrupt peer, we'll need to do something different. So that's my talk, and thank you for listening.
Good, thank you for a nice talk. So we are a little bit over time, but we do have time for questions still. While we're waiting for other, yeah, so I have a question from Daniel Escudero. He asks, how do you deal with the ring case in practice? He says, because the serialized proofs over rings require interpolation, which is expensive. And for practical circuits, the serial knowledge probably becomes the overhead concretely. I don't know if you agree with that, but.
So yeah, I don't know if I agree with that either, but I don't know because we haven't implemented it. You're right that the ring, we have to work a bit to to get the ring to have enough interpolation points. We do it by extending the ring to some extension ring that has enough interpolation points. It will be more computationally expensive than a field, but the semi-honest protocol will probably be less expensive than the field. I'm not sure. So I don't know how the savings in communication compare with overhead in computation.
Okay. Okay. I had one question which maybe you answered actually towards the end. So if we imagine the case where everything goes well immediately, so we just all the proofs are accepted, and now I have to reconstruct the output from a sequence sharing. So in order to do this, since the proofs did not say anything about the output shares, we have to be able to authenticate those, right? Is that what the authentication tags that you mentioned are for?
So no, the authentication tags are used to, if you're talking about between layers, between the blocks, then yes, that's exactly what they're for. The authentication tags are used to ensure that the output from block to block is consistent. So they're going to be added to the semi-honest protocol, and they're going to allow us to go back only a single block, and then we have a basis from that block to continue with authenticated shares. That idea can also work for the final output.
Okay. Good. We didn't get any more questions on the Q&A, so I suppose that was it. So thank you very much for that. We'll just take a 4 minutes break, just about, before we go to the next talk.
Okay, thank you.
So